So the purpose of this talk is just to help you guys, read through all the buzz and stuff you see on the news nowadays. Whether it's sensational outlines like graphene chips will provide 1000x performance and whatnot, to give you guys a realistic measure on what all this shit actually means and how hardware scales. I realize maybe one of you guys are actually in hardware, so I've made this as comprehensive as possible. And for those of you who attended the 4-hour version, I'm really sorry. But, I'm giving it drunk, so, it'll balance out, But yeah, a lot of hype. We'll talk about, some general ground rules of innovation and scaling, and how to tell at a glance whether or not a certain technology will scale, whether it won't. To basically, give you guys some intuition, right? Because we have a lot of different topics to cover today. Some of them are within my domain of expertise, some of them are not, so I'll talk about which ones aren't. Okay. And, like I said, all public knowledge, nothing sponsored. Like I said, the focus is mostly on hardware, but like I said, because it's AI and shit, I have to talk about quantum computing at some point, so I will. Not an expert, but I'll give you guys my 2 cents. And to give AI the best case scenario, right? A lot of what I say will be true even if AGI is achieved, even if AI, its learning is mastered, whatnot. Like some of these limitations will remain in place. So we're going to give AI the best case scenario it can possibly have. Legal or logical limitations put aside. That's the general through line. We'll talk about a lot of the hardware limitations, and then we'll mirror them onto the software side, the logical limitations, and then it should wrap together beautifully. So we'll start with some, methods of design, 2 main ones, and they will basically become like the through line for the entire talk today. So pay extra close attention when I talk about those 2. So, when it comes to designing, a general processing unit that can process any software, any software of any kind, right? There are 4 main parameters that are required, and a lot of these are extracted from the idea of a general Turing machine. The 3 means of control, reference, program, memory, right? A lot of these are extracted from the idea of a universal Turing machine. And the one in red there is basically a physical limitation, right? When you actually put this idea into practice, it's what you need to get this into operation, right? And you will realize that a lot of optimizations you see in hardware are actually closely tied to these 4 fundamental design principles. So, you can make a computer out of basically anything, right? As long as you got a means of control, some way to store memory, right? Whether it's using, biological systems, DNA, video games, right? Doesn't matter what your medium is for designing a processing unit, right? At the end of the day, as long as you got those 4 requirements, right, you can make a computer out of anything. So, when it comes to hardware optimization, as long as you optimize each of these 4 things, that's the most efficiency you're ever going to get out of a compute system. So a lot of today's hardware, cutting-edge hardware optimizations tackle with one of these 4. And we're going to talk about some of the hard walls you'll see when you hit each one individually and how they tie together. All right.
Are we reaching a point of diminishing returns with the improvements we're seeing in the hardware?
10 years.
10 years?
We'll get to that soon.
Okay.
We're all fucked. So, this is the through line for the entire talk, so pay extra close attention to this. So there are 2 main ways you can design any system, right? It doesn't have to be hardware, any logical system. You can design it top down and bottom up. And this comes back to bite us in the ass when it comes to nanoscale fabrication. The main difference between the 2 is essentially when you're designing a system bottom up, you have the base rules configured, you have minimal control, and it reconfigures itself into whatever configuration best fits the rules that you've defined. When you design something top-down, you have a central control mechanism or a central influencing mechanism that'll closely, design and control how things are arranged. That's just the main difference between the two. And this causes a lot of problems when it comes to scaling nanoscale designs. So, to give an example, right? Biology is very simple. A lot of the systems are designed bottom up, right? Physics, it's got some base rules, and then everything that's derived from physics follows up those bottom up rules, right? Same with biology. At some point in biological operation, you do have some processes that are more top down, where you have a controlling mechanism, whether it's your brain's hippocampus or any other mechanism. So there is a divergence from bottom up designs at some point in biology, and this can diverge. And biological learning, when it comes to the brain, right, follows a very bottom-up structure, right? You don't tell it exactly what to learn. It maps it in very much the same way a neural net does. And basically, so to give a quick simulation, right? Very simple stuff, right? So if you have a bottom-up design system, so if you're doing bottom-up design in a bottom-up system, very simple, right? You throw your actors or elements into the system, you have some ground rules, and it's basically a probabilistic convergence on whatever form is most efficient relative to the rules that you've set out, right? For physics, it's usually energy efficiency, right? So at a small enough scale, whatever configuration comes out will usually be very energy efficient, because that is the driving force of design, right? At larger scales, like I said, it's not very time efficient because it can take a long time to converge upon a resource and energy efficient model, but at small scales it converges very quickly and requires very little energy very quickly. But when you do top down, you'll need an indirect mechanism to actually control how these things come together, right? Whether it's like, nanoscale fabrication, we're using lithography or whatever, right? You have to have some external mechanism that helps you configure these things in a way that you want. And they may be energy efficient, they may not, but it all depends on how much energy you're willing to expend trying to get them as precise as possible, right? So the cost here is entirely on the mechanism that you use to get this thing to converge. So this is the main inefficiency when you have a top-down design method built upon a bottom-up system. Right. So, in the case of artificial complexity, in other words, hardware, AI, whatever, right? You see that we're layering top-down design methodology on top of bottom-up systems, and you have interlacing of the two. And this results in a lot of overhead, right? Bottom-up and bottom-up, easy, no problem. It'll get the most energy-efficient model that you can have at certain scales. But once you start mixing the two, top-down and bottom-up together, you will inevitably run into overhead. Like, this is unavoidable. There's no solution to this problem. There's no magical technology that will ever come along that will solve this problem. This is something you just have to accept, that this will result in overhead. And there are solutions to get around this, but they are not perfect. I mean, we've used some manner of biomimicry when it comes to AI, right? People have talked about, okay, we can use neuromorphic methods, make the hardware look like a brain, right? But at the end of the day, you're still, fabricating that thing at nanoscale using a top-down design method. Lithography, right, the technology used to actually design the hardware at nanoscale is a top-down methodology. There's no efficient way to do that, because the bottom-up equivalent is using evolution and reproduction. You're not going to use that thing at scale, right? It's just not a viable method, right? And some people have proposed it for hardware, and we'll get to that. But yeah, so essentially, that is unavoidable, right? That semiconductor fabrication being top-down is unavoidable. So regardless of if you use neuromorphic hardware or not, you're going to have overhead. You can't get around that. And when it comes to things that scale, right? When you have overhead, essentially the most common solution to overhead is to have modularity, right? When it comes to lithography, you have to use repeating patterns a lot. The more custom it is, the more expensive the shit's going to become. And it scales up very much so. So if you want it to scale up, right, with complexity, you need to use repeating patterns, you need to have a lot of overhead and modularity with that, and there's a lot of waste with that. This is one of the main reasons why artificial complexity will never bridge, biological complexity when it comes to efficiency in this manner. So first takeaway, got a lot of these. So because of the overhead you get from layering, bottom up and top down design methods, artificial and natural complexity, it's actually physically impossible to bridge the power efficiency between these two methodologies. That's something you're going to have to live with. And this will come back to bite us later. All right, so now let's actually talk about how hardware actually gets better, right? So remember, there's only 4 requirements to design a universal CPU. So at the end of the day, there's only 4 things we've got to optimize in order to make this shit actually work properly or work better, right? So we'll see the hard wall on each of these. So needless to say, this is a very long topic, and we're going to give you guys the general abbreviation version. So it'll be a quick overview. If you guys want like in-depth context and details, I'm sure there's a 4-hour version somewhere on YouTube. So we'll talk about the first one, right? So those four methodologies for designing a universal CPU map very nicely to these 4 design optimization problems, right? In terms of size of your compute unit, interconnect and routing, accelerators and data flow, and asynchronous paradigms. So we'll talk about each one of these. So this is one I'm pretty sure everyone knows about, right? You want to make things run better, you can make it run faster, right? What's the problem with that? Simple. You want to make things run faster. The heat and power consumption scales quadratically with that, right? You double the clock rate and it'll melt your CPU. You're going to be using liquid nitrogen to cool your CPU. So that's not a viable solution. You cannot, after a certain speed, you cannot keep on increasing and pumping up your clock rate, right? So you got to find better solutions than this. You can't run things faster. So, all right, you can't make things faster. Why don't we do multiple things at once? Increase the compute density, more cores. And that was basically the vibe of design for the last decade or so. So let's see where that got us. Like I said, everything at nanoscale is designed using lithography. And for those that don't know what this is, think of it like the 3D printer of nanoscale, right? That's basically what it is. It uses some very similar principles, right? Like scaffolding. It uses a material that reacts with light. You use light beams to basically design out the patterns that you want. And then you etch away that, and then whatever's left and filled with the material that you actually want is your design. As you can see, it's quite complicated, right? You go through all this shit to get a very simple geometry out of that. So if you make anything too complicated, you can imagine quite clearly how expensive that shit's going to become, right? So once you get to the nanoscale, a lot of geometry is very simple for this reason, because the more layers you got to stack on, the more prohibitively expensive this shit gets. And that's just one layer, by the way. So that on the previous slide was just the transistor alone. If you want actually the CPU on top of that, that's a bunch of metal wire connections stacked on top of that. So you got many, many different layers of wiring and connection, and then you get your overall die chip. So as you can see, this shit gets complicated really fast. And note, the bottom layer here, we just have transistors. We don't even have memory yet, right? So if you just have transistors, you're stacking on the metal layers and making your CPU. That's all this is. Memory is an entirely different pain in the ass entirely. And even this has got limitations, right? I mean, if you go to certain wavelengths of light, at some point, right, you'll reach a spectrum that'll basically pass through most matter, right? You're not going to have, because at the end of the day, in order to design at that scale, you need a material that reacts with light, right? You get to smaller and smaller wavelengths. It's really hard to find materials for which light doesn't just pass through, right? You get to a small enough wavelength, or influence in very negative ways, right? So at certain scales, like I said, lithography does reach its limit. So you cannot make things smaller indefinitely. This is a problem we hit probably about 5 years ago. So making things smaller is becoming more of a problem with lithography. And the other problem is, the smaller things become, the less likely they're to remain static, right? You get to the nanoscale, or you get to the atomic scale, these things tend to move around. They do not sit still. So it's very, very hard to build transistors and compute units that are stable, right? Because if things are always moving around a lot, it's very hard to predict what they're going to do. You can't make a computer out of this shit. So we can't keep making things smaller indefinitely. And what's worse, if you're hoping for some magical material to come along that'll solve this problem for you, well, for any types of complexity, we're not even talking about like silicon or hardware, any types of complexity, whether it's biological or artificial, there are certain requirements you need for your base element to be able to orient itself into very complicated configurations. I won't go through all this shit, but just take my word for it. That's what you need. And this is all the shit that we have. And if you take away all the shit that does not work, this is what we're left with. These are all the elements that we can actually use to make anything complicated, biological or artificial. So, we're not left with much. And the other problem is, like I said, we're getting to the nanoscale now, right? So, things are getting very small. You cannot use complicated compounds anymore because they're too big, right? Eventually, using a compound transistor will become a bottleneck in itself. So if you remove all the elements that are only used in compounds, we're left with 3. And the way this chart works in general is that the lower down you go, the less abundant, more expensive the shit is. So we'd prefer, I mean there are exceptions to the rule, but we'd prefer the elements to be higher on this table. So if you look at the top 2, it works out quite beautifully actually. You got carbon and silicon. One is the foundation for all natural complexity, and the other one is the foundation for all artificial complexity. And remember what I said about bottom-up and top-down design. The only differentiating factor between the two is how much control you actually have at that scale. So it wouldn't surprise you to notice that carbon has bonds that are very strong, very hard to influence externally. So it's naturally better suited for bottom-up complexity, whereas silicon is the inverse, right? So you can have a band gap that allows you to toggle things on and off, very easy to influence externally, and therefore you can use it in top-down design. So, remove the one that we can't use to design hardware, we got the 2 left. And these 2, silicon and germanium, are the 2 most common elements used in designing most processors. More silicon than germanium, but yeah. As you can see, like I said, not a lot of leeway. There's not much else we can use. So we are hitting a wall in terms of material science as well. But, you know, this wouldn't be comprehensive without talking about that magical buzzword that, you know, all the sensationalist headlines like to talk. So there's this really magic material that everyone likes to harp on about called graphene. You know, it's made of carbon, you know, that super special element we just discussed. It's one atomic layer thin, which is as thin gets. And it's in the form of a hexagon, which is on a 2D plane, basically the most condensed geometric shape you can have. So as far as special materials go, this is as special as a material can get. And basically, it's the magic material that everyone wants to talk about as if it's the future and whatnot. And we'll talk about what it can and cannot do. So, graphene, very good conductor. Carbon, not. Why? Because, like I said, it's a 2D material. On the third dimension, right, there's no bonds, there's no elements, right? There's a lot of freedom for the electrons to actually travel. So like I said, it makes a very good conductor. But that's not a very good transistor, right? It's very shit for toggling on and off. You can't, right? It's very good for conduction. So it's like you can't actually use this for computation. So like, okay, how do you use it for computation then? You actually have to layer this into this monstrous geometry, right? So like, you have to roll it up into this geometry to actually make it into a semi-decent semiconductor. And remember, at the nanoscale, when you're using lithography, you're printing one layer at a time. You are not printing this shit, right? Making this at the nanoscale is a fucking nightmare. All the methods used to make this shit are indirect. They use like chemical deposition. They're very slow. They're not top-down methods, they're bottom-up. So it's like, if you're going to design this shit, it's very expensive. This is called the carbon nanotube, for those who are aware. So anytime you see in the papers, you know, carbon nanotubes and whatnot, as a solution to semiconductors, you got to remember, manufacturing this, super expensive and super slow, because just look at it. It's not going to be scalable anytime soon. I guarantee you that. But that's not to say people haven't tried, right? There was a proposal to use carbon nanotubes and transistors, right? And because, like I said, it because it's much better at transmitting. It's a much better conductor, right? So it consumes less power. There's a lot less friction in that sense, right? But it's massive, right? That rolled up architecture, right? It's not going to become scaled as small as a nanoscale design ever, right? So even if you get this scaled up into production, right, it'll have better power consumption, no doubt, right? But the compute density will just never compete with frontier silicon. So there are always trade-offs. And, you know, like I said, they've got mass production going back in 2020. But like I said, if you ever see in the headlines anywhere graphene chip on the horizon, the two things to keep into account always are, okay, what is the cost? Because like I said, making this thing is prohibitively expensive. It's a very slow process to make this shit. And what's the actual compute density, right? It might be thousands of times better, right? Or it might be many orders of magnitude better in terms of power consumption, as they claim, which I highly doubt. But it might be. But those are the two metrics to keep an eye on. And they hardly ever mention them. And, you know, because it's frontier engineering, there's a lot of money. We're getting very desperate to find solutions to fix this problem. No doubt somebody had the bright idea to combine silicon and carbon. You know, like these are the only two options we got. Why not just smack them together? Maybe that'll solve all the problems. And to some extent it does, right? It's more resilient, right? It's got a better band gap, more control. But, you know, now that you're going from a single element to a compound, it is more expensive at the end of the day. So there's always trade-offs at the end of the day. So you got to weigh that. And the other problem is, remember, graphene is a super great conductor. It's a very shit semiconductor, right? So if you have if it's very hard to toggle and very hard to control in that sense, it's going to be very, very difficult to make a synchronous circuit out of that. So it's more suited for analog than it is for digital because it's hard to synchronize that shit, right? So if you see in the headlines, you know, any topic of graphene chips, do note whether or not they're digital or analog, because 99% of the time they're going to be an analog chip. And analog chips have very, very, very niche use cases. You're not going to see that replacing general purpose CPUs anytime soon. You're not going to see that in laptops. The most you're going to see that is maybe in a server as an accelerator. So, why did I go through all that? TSMC, the biggest manufacturing company in the world, right? Back in 2021, things got so desperate for them that they had to publish a paper where they actually had to explore using a different element altogether, right? They had to use a heavier element in their 1 nanometer fabrication process. This is something they were exploring. Because like I said, geometrically at that scale, you are reaching a dead end. There's not much more you can do, really. So if the biggest company in the world, and to give you an idea, this one is all the way fucking down here, right? On this table, the further down south you go, the less abundant and more expensive the shit is. So, and at their scale, the costs are astronomical. So if the biggest, most well-known fabrication company in the world is forced to explore a different element altogether to solve the problem of scaling down further, you can see how dire the hard walls on scaling smaller actually is becoming, right? Even IMAC, right, the institution that everyone looks to for pioneering the newest architectures for small-scale hardware and designs, right? I mean, they've said many things here, but if you read past the waffle and whatnot, basically they say they have no idea what the fuck they're going to do after CFETs. They're exploring 2D materials, which is basically materials like graphene. And as we've just discussed, graphene is a shit semiconductor. So, that is to say, I would say probably in a decade's time, 2035, you know, I would expect scaling down to basically hit a hard wall in terms of performance increases. So we're gonna, even if we do find some innovative solutions, they have trade-offs. There's no perfect solution here. And a lot of the solutions that we did find, you'll find that it's not something that we've come up with in the recent years. So, second takeaway, you know, we're reaching a dead end when it comes to making things smaller. And if you go if you try to run things faster, it's hard to synchronize that shit. So you're going to become more analog than you are digital. This is something you're probably going to see by 2031 or so. All right. So yeah, that's the dead end for size. But, there are other ways to make things more efficient, right? We got interconnects, we got memory, routing, and whatnot. Let's see where we can do that. All right, so we can't make things any better by shirking on 2D. So there are certain options here, right? Somebody's like, well, we can stack things up on 3D, right? I mean, 4D is not a thing, but at least we have 3D. And, wiring, when it comes to hardware, is actually where a lot of the power consumption is. So if you make that shit smaller, you can save a lot of power, right? So these are the two different approaches we have to actually increasing performance when it comes to routing. And they both have some major pain in the ass bottlenecks. So if you were to look at, a standard chip or SoC, you would have some common components. You got your I/O, you got your compute, memory, whatever, right? And you'll notice, maybe you might be wondering, why aren't they all together in one big chip? Why even have them separately like this in the first place? Money, right? It costs a lot of money to make these components. So usually what you do is all the critical components, like the compute, you have them on the smallest possible node possible. And the less critical stuff, maybe I/O, you would maybe have at a larger fabrication technology. So they're just not made at the same size, right? You might have one at 2 nanometer, one at 10 nanometer. So that's why they're on separate dies altogether. You can't mix the two together. And that's the simplified version. In an actual chip, you'll have more than one of these things. So you might not have one compute node, you might have up to 4. And you're like, okay, well, why the fuck don't you just combine these together, right? Why do you need 4 of these things? Well, the bigger your chip gets, the more likely you're going to have a defect. Because remember, we're tinkering with shit at the nanoscale, right? So it's very, very likely you're going to mess up at some point, and it's very, very sensitive, very, very finicky, right? The larger things get, the more likely you're going to have a defect, and the more expensive your process is going to be, because you got to, there's a lot of waste there. There was a company that tried this, Cerberus, and they basically, to get around this problem, what they had to do is they had to add a lot of redundant hardware, right? So essentially they had multiples of different hardware units. So if one is defective, they just route it to the other one. But as you can see, that's a lot of waste, right? So it's not a perfect solution. So you can't make them bigger beyond a certain scale either. And, when it comes to stacking things 3D, there's certain things you can do, right? You can stack the memory and compute and the I/O on top of one another, reduce the amount of wires you need, and this is a solution, right? And different companies have different solutions, right? You got the AMD solution, you got the GraphCore solution, where they're all integrated closer together, but obviously that's a lot more tricky and more expensive. And you got the Intel solution, where you basically just take the transistor, 2 components of the transistor, and just flip them on the head. And notice here, you're just stacking them. You're not really increasing. You are decreasing the amount of routing you need, right? But at the end of the day, your density, your compute density is quite high. You also have to cool that shit, right? So cooling is becoming a major problem because, it's not so much cooling the entire unit. You got to cool very specific areas of your chip, right? Otherwise, they will melt. So you got to find more creative cooling solutions. You can't use standard fans anymore. You got to use liquid cooling or laser cooling, right? So it's getting more and more difficult to cool this shit as well. So that's a big problem with stacking, right? So different solutions. At the end of the day, they accomplish the same thing, but to let you know. So that's the problem with stacking, right? Cooling is becoming a problem. It does increase your compute density, decrease your overall power, but at the end of the day, depending on how much you can cool it, there's only so much you can stack. So that's the hard wall on stacking on the 3rd dimension. And then we have this pain in the ass called memory. So with memory, right, you got 2 types of memory, right? You got your storage, and you got the memory you can actually use in operation, right? They have different optimization goals. When you're talking storage, it's just how much can you cram into this amount of volume you've got, right? You can use different encoding techniques to cram as much data as possible. Like I said, there are different mediums. We used to just write stuff down. You can encode it in magnetic fields. You can encode it in very different ways, right? So it doesn't really matter. You can use anything for memory. The only thing you got to keep in track is how easy is it to read from that shit. If it's too difficult, it's storage. It's not working memory, right? Conversely, working memory, like I said, it's very easy to read that, but a lot of these systems are dynamic, right? So they are always in motion, so very quick to read and write from, but that shit is huge compared to storage, right? Storage can condense a lot of data into a very small volume. Working memory is the exact opposite, right? It makes you read write super fast, but you just cannot cram a lot of data into the same amount of volume. So there's trade-offs here. And when it comes to AI, the only one that we give a shit about is the one in the middle, DRAM. It's the only one that's got trade-offs for both of these. You can use it for active memory, and it has a density that allows you to store those gigantic-ass neural networks that we're all working with. So the main bottleneck when it comes to neural networks is what can DRAM do and what it can't do. So we'll talk about that. All right, so this is the biggest pain in the ass when it comes to AI. You cannot mix memory and compute, right? Think about it this way. When it comes to memory, it scales better the larger your capacitance, the larger the size of your memory cell. When it comes to compute, you want to make things smaller. They have very different optimization goals. One is trying to make things small, one cannot work after a certain size. So if you try to cram the two different types of cells together, you essentially result in that, right? If you try to have one chip that has both memory and compute in it, remember, when you're designing stuff at the nanoscale, you cannot customize this stuff too carefully. You have to use a lot of repeating patterns. You have to use lithography, which has masks and whatnot, right? So if you cram memory cells and compute cells together, you will inevitably have a lot of wasted space, right? And that is very, very expensive because you have to use two different lithography masks to even design this shit. So this is one of the main reasons we don't have memory and compute on the same die. And the other problem is even if you have memory on its own die, its own die, DRAM, in order to get it working, it has to be refreshed at certain intervals. Like DRAM only works if it stays charged, but over time it loses charge, right? So essentially there's a constant power draw on this thing. So you can stack it many different layers higher, but that's just more power consumption, right? And we've got different protocols for this, HBM3, HBM4, but we are reaching a point where stacking any more DRAM cells is not viable. You guys might hear, okay, there are these large LLMs now, we've got these 2 trillion models and whatnot, but there might only be a couple hundred billion parameters that are actually active at any given point in time. And there are a couple of reasons for this. Well, I mean, power consumption is one, and not all the neural network parameters are relevant to your problem. But this is also another factor in that. When it comes to actual cards on your server rack, they're heavily limited by the amount of DRAM cells you can stack. And usually they peter off at somewhere around 256 gigabytes of DRAM per card. So that's one of the major reasons why you don't really see more than a couple hundred billion parameters of your neural network active at any given point in time. Major bottleneck here. And there's no solution to this problem either, by the way. Just in case I haven't made that clear. So yeah, hardwall next. So essentially, 3D stacking, bottleneck by cooling, and memory is basically, there's no solution to cramming, for active memory, by the way. Any optimization you see in memory nowadays is for storage, not so much for active memory. Because beyond a certain size, it does not work well. You cannot make it any smaller. So you cannot get a lot of memory density solutions nowadays. So yeah, that's a dead end. Any other options here? Well, we got these accelerators and data flow. So this is the third parameter we can optimize for. Let's see what we can do with that. So back in the day, this is what your CPU execution flow would look like. You got your memory, you got your general compute unit, you got your software, right? A list of instructions, very straightforward. It's got a lot of problems with it, right? There's too little data being sent from memory to compute. There's a lot of instructions here, right? And you got to go through these long different fetch cycles, right? So a lot of the optimizations you see are basically revolved around these very, very basic design principles. So, GPUs came along, you can send more data at once, right? You have the same amount of instructions, but this is a very general abstraction, by the way, just to give you guys an idea. Obviously, it's more complicated than this, but yeah. So, with GPUs, you send more data, same instruction size, everything else remains the same. So that was the first optimization. And then we were like, okay, instead of using very simple instructions to do a very complicated task, why don't we have specific hardware that does that? So instead of using addition instructions to do multiplication, why not just have hardware that does the multiplication, and you'll reduce the instruction set. Great, you brought down the amount of instructions you need, but you still got this gigantic fetch loop. And notice you're using both the GPU and CPU. You got to synchronize both of these two things. And that's just for a multiplication application, right? In a standard neural network, algorithm, right? It's not just the matrix multiplication that matters, right? You also got stuff like rectification, normalization, right? That's not going to use the GPU matrix multiplication as much, right? So you might have dependencies between your GPU and your CPU, right? Now you got two different feedback loops going, right? You're sending all the matrix multiplication to the GPU, you're sending all of the other applications to the CPU, and now you got to synchronize the two different feedback loops. Very, very, very inefficient. So I was like, all right, can we fix that in some way? Well, the Apple M chips came along, and they're like, okay, what if we just unified the memory, right? Instead of having separate memory for CPU and GPU, why not you have the one? Right? I was like, all right, bit of an improvement. You still got the two different feedback loops that you need to synchronize. So it's not the best solution. And then it's like, okay, so that's all a major pain in the ass. Why not just use FPGAs? Those reprogrammable boards that can become basically any hardware that you want. Recall at the beginning of the talk, right? So FPGAs, they pretend or mimic to be a bottom-up system, right? You can map any hardware you want. But at the end of the day, they're still fabricated using top-down technology at nanoscale, right? That overhead has not been fixed. So when you have a bottom-up architecture on top of a top-down fabrication process, that overhead results in a lot of power consumption. So FPGAs are very power hungry, right? They can get you the performance that you want, but at the end of the day, they'll expend a lot more power in doing so. So they're not a perfect solution, right? That's not to say they don't have any use case, but they're not going to fix this problem. But let's say we did cram an FPGA in there, and there are some hardware out there that do this, right? They have compute CPUs, and they also have FPGAs on the same chip, right? So you can get the best of both worlds. And ideally, this is the goal, right, that I see in terms of architecture when it comes to data flow, right? You want to reduce the instructions as much as possible. One instruction does everything, right? All right. So instead of having, long fetch cycles where you have to go back and forth, right? And you have to have multiple instructions to do so, why not just weave them all together like so, right? You can have the compute units, and you can have the very specific RTL to do the operations, but just cram an FPGA in between to do the stitching between them. So that way you don't have to go back to memory, you don't have to go back to your processor, and it can become a gigantic pipeline. This is the ideal form of execution on hardware for instructions. And I do see this being the direction that a lot of hardware for AI going in the next coming years. So if cards like the ASIC from AMD and equivalents are probably going to become more prominent in this area. But that is the limit in terms of data flow. Like, you can't get much better than that, really. And then some of you might be wondering, okay, if you can just do that, right, why don't you just map the entire AI algorithm onto hardware, right? Just have a hardware transformer, right? Like, that's the best option available. And the simple answer to that is money. It's expensive. Beyond a certain point, it's not economical to map your software onto hardware, right? We did it for matrix multiplication because you can use that for a lot of shit, right? You can use that for graphics, you can use that for AI. And we're doing more and more for AI, but eventually you're going to get to a point where different LLMs, right, are going to have different parameters. They're going to be scaled differently. You're not going to be able to map your entire logical architecture onto AI, onto hardware, because it's just not it's not economical to manufacture at nanoscale an architecture specifically for that, manufacture hardware specifically for that architecture. So there's going to be a diminishing return on this shit. And future talk, but we don't have time for that. But yeah, essentially, we're going to ignore any power management issues with any of this, because with AI, we want to maximize utilization, right? So we're going to assume, for the purpose of this this use case, that utilization is 100%. So yeah, that is the fourth takeaway, right? So basically, when it comes to mapping onto hardware, eventually economics is always going to bite you in the ass, and you're going to have to stop at some point. And that is where we're hitting our next hard wall in terms of AI. So, all right, we've hit 3 hard walls here. This is our last chance at making, better hardware for AI. What can we do with asynchronous paradigms? And my God, is this a nightmare? So let's get into this. I need a drink. All right. So there is a reason why a lot of the new hardware paradigms or innovations you guys see in the news nowadays was not talked about in the last 3 decades. It's because they didn't have a use case, right? Analog computation was used for digital signals processing, but it was useless for a lot of broad case computation for a reason, right? Analog is very lossy, it's very messy, it tends to have a lot of errors. You cannot use it for a lot of digital computation. So it wasn't until AI came along that a lot of these, newfangled paradigms of photonic computation and neuromorphic computation, they did not have a use case until AI, and they don't have a use case outside of AI. So that was the reason. It's not that we didn't think of them until now, because a lot of these so-called paradigm shifts were researched and published 30 years ago. It's just they hadn't found their use case until AI. AI is the only application besides DSP that can tolerate a certain amount of error in its computation. If you use it for standard computation, errors can result in fundamental breaks. I'm not going to spend too much time on this shit because, you might have read about, using brain on chip or organic computation or gold nanowires or plasma or all this shit. So all I will say about this is that if you remember from the very beginning of this talk, right, these are all bottom-up design methods, right? They may give you more efficiency and performance. I guarantee they probably will, right? But these will not scale, right? There's no way to make these scale. Bottom-up design methods will never scale to the same level that top-down methods will do in nanoscale fabrication. So we won't spend too much time on these. Their use cases are very niche, very, very niche, so not much to explore there. And if you see anywhere in the headlines anything about reversible computation, that is purely theory and theory alone. But the one that I will somewhat talk about, because at some point someone always has to bring up quantum computation, right? So, like I said, I'm in hardware. I'm not an expert on quantum computation. I'll just give you guys my 2 cents. It's pretty useless, and it probably will never be useful for AI. The only thing quantum computation could be used for in terms of AI is not inference, but training. And even if you use it for training, at the scale that you actually need it for training, it will decohere. This will probably never be able to scale up that much because the heat and the error correction required to get to billions of parameters is astronomically high. It breaks down if you get anywhere near that. There's a lot of feedback loops when it comes to AI. And as you know, quantum computation does not like feedback loops. So that's all I need to say about quantum. But, this one always comes back. Everybody loves fucking light computation photonics. So we'll talk about this one, right? So light is awesome. Great for transmission, dog shit when it comes to computation. And mostly because light is very, very hard to interact with. When it comes to electrons and electrical computation, they behave as a particle. Very easy to influence, right? You can toggle them on and off, right, depending on the architecture. With light, it's so much more difficult. The only way to influence light is to actually change the geometry of the material that it passes through, right? And because of that, a lot of the different hardware that's designed with light in mind uses these materials called phase change materials. And these things are a nightmare into themselves. So yeah, great for transmission, shit for computation. That's all you gotta remember about light. And the thing about phase change materials is, think about it this way, right? These materials have to constantly change their geometry. Something that's always changing all the time is going to have very, very dog shit durability, right? If you see any paper on light computation, not transmission, always look for, okay, what's the durability on this thing? Because they never publish this. There'll be like a tiny snippet at the end of the paper on how durable this shit actually is. I think the best durability we ever got was like 100,000 clock cycles. You imagine a CPU, you know how shit that 100,000 clock cycle is. You're gonna be swapping these things out every minute. So, and there is no alternative, by the way. You want to interact with light, you have to do this. And by nature, phase change materials have to have shit durability, right? Like this is an unsolvable problem, right? So you cannot use light for digital computation. You can use it for transmission, but that doesn't mean it's completely useless. Like, we'll talk about some, because there is a caveat, right? You can't use it for digital, but you can use it for analog, right? Because in analog, you don't have to toggle as much anymore, right? You're not synchronized to a clock, right? So even though those phase change materials are dog shit when it comes to durability, if you don't have to toggle them so much, right, they can last much longer, right? So they do wonders when it comes to analog computation, right? You have your circuit design, you don't need to change it all that often, right? And you do the same algorithm over and over and over again, and you don't need to toggle as much. It's found its niche use case. That's why light is in the news nowadays. Otherwise, nobody would touch this with a 10-foot pole. And, all right, so it's like, okay, you can use it for math, right? So why not just have best of both worlds, right? You have your CPU on electrical, and you have your math on optical, and just put them together. Well, you want to do that shit, you got to have a conversion, right? Because if you're going to use analog and you're going to use digital together, you have to convert from analog to digital. At a certain scale, this is okay, right? If it's like, for example, it's already done in servers, right? They have like analog interconnects, right, for transmission, and then you have electrical processing. No problem there, right? It's not much of an overhead. But you get to a point where it becomes a complete nightmare, right? So if you're going to have it integrated into the chip itself, right, the number of analog to digital converters is going to skyrocket, right? At a certain scale, it's just not viable, even for transmission, to use light, right? You got to be very, very, very decisive on at what scale you're going to use this, because the analog to digital conversion gets to an extent where it will negate any efficiency increase you will get from using optical interconnects. So that's the hard wall on light. And well, this is another buzzword that shows up in the news every now and then. Neuromorphic hardware. Oh my God, this is such a pain in the ass. So, all right, if you make it a large scale, it makes perfect sense. But remember, in order to get the shit to scale to the front and cutting edge, look what you actually have to do, right? Neuromorphic is basically trying to mimic the same architecture the brain has, right? You got your neurons, and you got the interconnects between the neurons, and you just map that to hardware. Simple enough, right? But at the end of the day, how are you going to map a neuron to hardware? It has to be in the form of a DRAM cell, right? If you try to mix DRAM and standard computation, we already discussed, there's a lot of wasted space there, right? It's not the most efficient integration. So a lot of neuromorphic hardware, if you ever see this in the headlines, one thing to keep in mind or look for is how small is this hardware actually, right? And one thing you'll find is that, okay, in all the comparisons they will do is at relative scale, right? They'll never compare to the cutting edge, because neuromorphic hardware is not going to ever be as small as traditional nanoscale fabrication. And, okay. And then the last thing we'll ever talk about. So we work wonders when it comes to, power efficiency, because biology, right, it doesn't really differentiate between compute and memory, right? We can do both of those things. Amazing, I know. And most of that, it's a wondrous property of bottom-up design when it comes to natural complexity. So then the idea was like, can't we just do that shit with artificial complexity, transistors and shit? It's like, all right. There's got to be that mythical fourth material that can act as both, a resistor and a capacitor, right? You got a memristor, so it can be both memory and compute. And it does exist, but remember, you're trying to get a material that acts as two very, very different properties. So, by nature, that takes the form of a phase change material. So, by nature, that is going to have very shit durability. But yeah, constant reminder that physics is a bitch. There is no free lunch here, guys. So yeah, fourth takeaway, analog computation, very niche use cases. It'll only ever be used for either accelerators or on edge, It just cannot be used for everything. It was completely useless before AI came along, except for NLP, the DSP, I guess. So yeah, that is the four hard walls when it comes to hardware shrinking and whatnot. So let's tie all this shit together and see how it comes together. I won't talk too much about, servers and trade-offs and whatnot because it's not too much my domain, but, main focus here is, okay, what is the cost for inference? Because I'm trying to give AI the best case scenario. So we're not even going to talk about training that much, right? Because for training, you want throughput. For inference, like I said, okay, how much compute can you get for certain power distribution, right? So that is a goal here. And well, like I said, cooling is a major factor. We're not going to get into that, but like I said, it is prohibitive. We're going to give it the best case scenario. We're not even going to talk about depreciation, and that's an economic nightmare in itself. Yeah, OpenAI is royally fucked. Okay, and I won't talk too much about fusion, but it comes into discussion a lot, all right? So, yes, it is technically more efficient, and yes, it will make energy prices cheaper. So it's like AI will become cheaper, but at the end of the day, guys, it's still bottlenecked by transmission, right? It's at the end of the day, it's still not going to make energy free, right? Your transmission rate is still a thing. So although it will reduce the cost without reducing the power consumption, it's really not going to affect anything that I'm about to say that much. So yeah, nothing changes if fusion becomes real. Trust me. So the hypothetical best case model, right? If you're talking about edge use cases, if you can get an end-to-end analog processing unit, there's nothing better in terms of power consumption, right? So if you can sample all of your signals and sensors in analog, process them in analog, spit them out in analog, wonderful, right? Saves power, very efficient. You're never going to be able to do that shit on server. On server, the most you can hope for is like some kind of glue logic where you have, you have a general purpose CPU, you might have some accelerators that might be analog, might be photonic, right? Slot them in there, have some analog to digital conversion, and then you're going to connect them, stitch them together using maybe an FPGA or optical interconnects. This is the form of the ideal server for AI. And yeah, of course, there's memory restrictions. So if I had to give a prediction, maybe 2036 is when I see all of these things integrated into a server. All right, so that was the hardware shit. Let's map it onto the software side. Let's talk about learning in general. Because there's one property of learning that you just cannot take away for any AI architecture whatsoever. It doesn't matter if you use a transformer. It doesn't matter if you use anything else. There's one thing that all learning needs, and that's correlation. And correlation mapping is quadratic in nature, right? Simple property. Yeah, you got two things, you want to correlate them together, fine. Great. But once you get more and more, if you don't have a crossbar where you're correlating all of your inputs to your outputs, you are having correlation loss, right? At the end of the day, whether a property like, if something is going to be ripe or not, can be tied to shape, can be tied to color, right? If you try to abstract that out, at the end of the day, you're losing information. So one thing that you cannot take away or cannot assume when it comes to learning is whether or not all your inputs are going to be correlated to all of your outputs. You just have to assume this shit. And you might have seen, many different transformer variants, like, this transformer variant is X times more efficient than what you've seen before. But you'll realize that a lot of these optimizations and these variants, they usually take away from some sort of, they usually have some kind of correlation loss. Because they have to have some kind of linearization in the algorithm to get any kind of savings. Because the quadratic nature of learning, you can't get around that. So in general, you map everything to everything else, scales up quadratically, and just why learning is so expensive, right? You can't get around that. especially when it gets deeper and deeper and deeper, right? Context and whatnot, right? So that quadratic scaling is going to be a bitch regardless of whatever architecture you use. Like, you can't get around that. So it's going to be expensive. And correlation loss, although it's bad, it's something that you might actually have to deal with to make things economical, right? And that's what they do, right? OpenAI, Google, whatnot, right? You'll separate things based on domains. You'll have arbiters that will choose between those domains, right? And with every single separation, whether it's modalities, whether it's expertise or domains, you're going to have correlation loss. Because at the end of the day, this input is not correlated to this input in the output, right? There's some oversight there, right? And one prime example is, like, remember the early LLMs were dog shit when it came to spatial reasoning. Why? Because they were trained on text, right? And they were trained on images, but they weren't trained on them together, right? So the arbiter that put those two things together had no idea what spatial reasoning would look like, right? So that was a very easy use case. But it's the same way, right? If you try to correlate biology and chemistry together, you might have some kind of oversight because you weren't trained on them together. And you have to do this, because if you try to map all these together, the cost is going to be so exponential that OpenAI will go bankrupt within a week, right? So that is the fundamental limitation on implementing any AI. Cost will not allow you to put these things together. You have to decide where you're going to cut this in. So, if this is your entire domain space, you might divide it between modalities, you might divide it in terms of expertise or whatnot, right? And then, if you have inference, right? So, okay, you have low-level features, and then you have arbiters stacked on top that basically tries to combine all this shit together, right? And then, remember, all this partitioning is done by human intuition, right? These things might have nonlinear correlations that are very, very, very difficult to intuit, right? But we use human intuition to break the shit apart. And that works sometimes, that might not work a lot of the times, right? So there is no getting around the blind spots that this will introduce into your inference. And do take note of what shape that is, right? No matter. Because if you ever want to make a problem a pain in the ass for any AI, all you got to do is prompt in this shape here, right? It's a contextual pyramid, right? You have a very, very, very specific thing that you're looking for, but the context needed to get to that very specific thing has a very wide foundation, right? A lot of interdependencies, feedback loops. If you frame any problem in this shape, I guarantee you it'll be maximally expensive for any AI out there. And it's precisely because of this arbitration that you have to go through. And ironically, that's actually the ideal career progression for humans as well. So if you work at any organization, right, you might start with, okay, you learn the basic languages in uni, you get into the industry, you learn the tools and API, eventually you'll learn the company's internal flows and low-level config, and you might get into high-level architecture. It follows the same contextual pyramid, right? So there's a mirroring between AI and humans beautifully in this dynamic here. It's one of the reasons why I always say that, general LLMs is the dead-end career, because look, how often do you need to update that shit, right? So if it gets as good as it gets, most of the work that you're going to get in terms of longevity is going to be from fine-tuning for a very specific project, right? Like, you can design it for the industry standard, but that's not going to be changed every couple of years. And there's another problem. This is usually the problem with AI generators, right? Everybody likes producing AI shit. Nobody likes consuming AI shit, mostly because of this, right? So if you work for a new company or you're designing something from scratch, AI generators are fantastic, right? They can design a lot of shit from scratch, no problem. But as your design gets more and more complicated, or if you work for a company that's got like a lot of legacy API, millions of lines of code, right? The thing that you want is going to become more and more specific. Your specification is going to grow in size over time, right? And your implementation is going to be smaller. You might only need to make a very, very small adjustment to your code base. So eventually you get to a point where your specification is more complicated than your implementation. So you might as well just make the change yourself. And AI generators have a very much a diminishing return if this is the domain space, if this sort of paradigm maps to your work, right? If your job is one such that your contextual pyramid grows over time, this is the ultimate fate of any AI generator you will adopt internally at the company. Useful at the beginning, completely useless at the end. So, even if you do fine-tune these generators on like your own code base, you gotta ask yourself, how often are you gonna do that? Once per project, right? Once per milestone? How much is that gonna cost you, right? At some point, it is inevitable that these things will have a diminishing return. And if you look at corporate hierarchies, right? If you want to say, okay, generators no-go, single LLM no-goes, well, what about an agent swarm or something like that? Or remember that correlation problem that we discussed with before? Well, it just translates itself into a communication bottleneck now. Same problem, different form, right? You have a protocol with which you're communicating between different agents, same way in terms of human hierarchy, like it's a mirror, right? There's only so much you can say in a certain way, right? You're definitely going to lose information, you're definitely going to lose intent, and this is unavoidable, right? You got these bottlenecks in agents. So the same problem just, translates itself into a different form. And this is why, the customer might want something, and at the end of the day, you might get something completely different because, the way management sees it, the way technical sees it, the way legal sees it, by the time it gets into production, it might not look anything like the original vision because that communication bottleneck really does come back to bite you in the ass. But that's not to say there isn't some merit in that. I will say if you're looking for a company that scales well, one thing that I always say is try to find a company that embraces bottom-up hierarchy well. Because you want to be in a company for which your work, the contextual pyramid grows in size. Because if you don't, that's when you're challenged by AI, right? And if your contextual pyramid is going to grow with time at your company, eventually you're going to get to a point where the thing that you're designing is so complicated, it's not practical for the guy at the top to be aware of all the design details for the low-level IPs. So eventually, this is a good measure. You should get to a point where negotiating power should go from the top architecture to the low-level IPs, because at the end of the day, they understand best what their IP can do or what they can't do, right? So negotiation is more bottom-up than it is top-down. That is the complexity ceiling when it comes to organizations, I would say. Something to strive for. So yeah, next takeaway. Quadratic scaling is fundamental, can't avoid that shit, and you cannot avoid compression and correlation loss because it's the only way to make this shit practical. All right, and that's just talking about LLMs, right? I'm pretty sure it's not common knowledge at this point, well, it is common knowledge at this point, that LLMs alone do not reach AGI because there are a lot of other complicated functions to mimic, right? Sure, transformers might have been modeled after the brain hippocampus, right? It's a very close mirroring. But that doesn't mean that just using LLMs alone, you're going to get AGI, because there's a lot of other very complicated processes that happen, right? Like in human beings, sleep does a lot, right? Sleep is what consolidates short-term memory and long-term memory, right? The AI equivalent is, okay, what? You're going to retrain this shit, you're going to fine-tune this shit, right? We don't do a lot of that because, one, it's expensive, right? And if you want to get close to AGI, like none of this is stuff that, these large companies like Google and OpenAI, they know this is what they need to get to AGI. The reason they don't do a lot of this shit is because it's expensive, right? You try to implement all these feedback loops, all this consolidation, if they're losing money now, you implement all this, they're going to go bankrupt in no time.
Do you think that as our understanding of neuroscience and our brains from a biological perspective improves, maybe partly because of LLMs or AI, but do you think that that's going to spearhead or push the next shift of innovation?
I mean, it'll fund neuroscience because obviously they don't have a lot of money to begin with, right? But if you're asking if that's going to help with AI development, right, you're not going to get around this problem of memory, right? So even if, think about what is innovation really, right? if you really boiled innovation down, it's factorization, right? You want to improve something, it's actually just factorization at the lowest possible level, right? And there's only so much you can factorize problems, right? If you cannot get around these feedback loops, for which some of them there are no problems, there are no solutions, right? You're just gonna have to bite the bullet and understand that you have to increase the power consumption to get that performance. And whether or not the economy has the margins, to accommodate that is something I cannot say, right? That's for an economist to comment on. But you just can't get around. Even if you factorize this problem, you can't get around the fact that it's gonna cost a shit ton more memory, a shit ton more money to do this. Synthetic data, like I said, this just made my brain hurt the first time I heard about it. It's like, all right, you're going to reinforce some of the same biases and it's going to somehow improve your AI? Fuck no, right? One common thing about simulations is simulations always have a lower resolution in the environment in which they are built, right? You make a simulation within a simulation, it's going to have even lower resolution. So any data that comes out of a simulation is going to have gaps in its understanding that if you train an AI on that, it's not going to be one-to-one with the real world, right? It's going to learn things that are not going to scale well. So basically, TLDR, AGI is capped by those things. They are not news to OpenAI. It's just they don't have the money to fund half of the shit. Okay. So, if we take the 4 design paradigms that we discussed at the beginning, mirror them onto the software side, talk about the 4 problems with AI, essentially these are the 4 requirements you need to have an AI-proof job, right? This will exploit the vulnerabilities on any AI there is, right? As long as you got a contextual pyramid of which your job can be mapped, as long as your job has environmental bottlenecks on throughput, right? So that specification becomes higher than implementation. As long as your error rate or tolerance for error is low enough such that you actually require your intuition, and as long as your performance and production cycles are short enough, then you cannot use an AI for that. Because like I said, AIs, if you're going to use it for a very specific project, they need to be retrained, right? It's not just the latency and inference we're talking about, it's the retraining cycles as well, right? So eventually you're going to have to weigh against, okay, retraining versus production cycles or latency versus real-time performance, right? You need all 4 of these criteria. Trust me, give it 100 years, your job is basically AI-proof. And that's basically what the slow graph is all about, You do the intersection, there you go. So, I'm not going to spend too much about this, but physical jobs are even more secure than knowledge-based jobs because I will tell you this now, batteries and degradation are much more of a bottleneck than AI ever was, right? Battery science has hit a wall many, many, many years ago, right? If you want to increase battery capacity, right? Capacity, charge, durability, all this shit, right? So if you want to increase that, there's only a limited number of materials that you can actually use for this shit. A lot of the problems, this is a very beautiful parallel, that you see at the macro scale, you'll also see at the micro scale, right? You have large different canyons, if you have water flowing through it, right? It's going to erode over time. Erosion also happens at the micro scale as well. It's just a very different way. This is one of the reasons solid-state batteries never work. Well, they work, but they don't work for very long, right? The more rigid something is, right, over time it's going to degrade and erode very easily. And if you're talking, charge capacity, right? There's a very few elements that are actually very, very suitable for this, right? You want to get small. You want to go smaller. You want to increase your energy density, right? Well, this is what we use now, lithium. That's pretty much as good as it gets, really, right? There's not many better solutions. I mean, hydrogen is known to explode, so trade-offs. As far as energy density goes for batteries, we're not really getting that much better in terms of material. We might get better in terms of geometry, though, which is something people explore, right? People have explored using carbon nanotubes sprinkled throughout your battery to get it to react better, or to get more, like I said, to get more reactions out of it, to increase the density and whatnot. But even carbon nanotubes, those things that were super expensive to manufacture, by the way, right? They only increased battery capacity by about 75%, based on a study back in 2022, I'd say. So there's really not much you can do in terms of geometry either, right? So if current batteries are hitting a wall, and geometry is hitting a wall at 75% better battery capacity than a lithium ion one, then I don't need to tell you guys that humanoid robots are the biggest marketing waffle you've ever seen in your lives. Because, robots work better when they're specialized, very specific function, right? You won't find much use cases for humanoid robots other than a marketing gimmick, really. Because you add more limbs, you add more degrees of freedom, that's more power consumption, right? Batteries aren't getting better, right? So all these humanoid robots you'll see will have at best a 1 to 2 hour battery life. They're not getting much better than that.
But what if we plug in the rocket?
If you're going to plug it in, why do you need limbs, right? Give it wheels, right? Make an assembly line, right? We had this shit for decades, right? You don't need a humanoid robot, right? It's purely a marketing gimmick, right? The only time you would need something with limbs is if it has to be field work, right? Not in a factory. It has to go out. That's why those dogs for the military have some use cases, right? You would actually get some, use case out of the limbs there, and you can't plug that shit in, right? So you got to be very wary when they tell you about this shit, because like every single one of these limbs increases the power consumption a lot, right? And that's just not going to scale. And remember, all of this is fabricated on a top-down design process. By nature, these things cannot self-repair and they cannot self-replicate without losing resolution every single time they do. Think 3D printer designing a 3D printer. Every single time you do it, the result is not as good as the thing that designed it, right? You're always going to have loss here. So, next takeaway point. We'll wrap things up, Jobs have taken many different turns over the centuries, right? Went from stability to access to information to specialization. I will tell you now that AI is not a job multiplier. It does cause convergence by its very nature, right? It condenses the contextual space that you need to learn. But will it take all jobs? Fuck no. Like I said, if you want your job to be AI proof, you just need those 4 parameters. Map into many different domains, right? Like some domains by nature are safe, right? Whether it's through legal, bureaucratic, or even natural hurdles, right? And it goes to say that you can clearly see one domain got fucked a lot harder than the others. But that's not to say it's completely hopeless for the artist, right? So it's just a matter of finding the appropriate bottleneck for each of these parameters, right? You chase that higher contextual domain, you find a platform that does not allow you to flood it with slop and curates for you, and even artists will find jobs post-AI. So next takeaway point. And it's quite funny that all companies eventually have to tackle one big problem, is that you cannot remain a product-based company forever, right? You can do R&D, you can do improvements, you can do factorization, but factorization does have a limit. Eventually you hit a point where you cannot improve a design, and all design companies need to transition into service-based ones. So I find it quite funny that if we ever end up with a model where hardware becomes a design as service industry, we're basically coming full circle from back in the day when we used to have women doing computations as calculators to engineers basically performing design as service, maybe on those FPGA mapping, right? Like you have firmware updates, you might have FPGA updates that are mapped to the algorithm. So very beautiful parallel. And predicting the future is not easy, right? There's a lot of non-linear relationships, right? The further you get away from your own domain, the more uncertainty you have in your predictions, right? So that is one thing to take into account. I'm a hardware engineer. I'm not an economist. I cannot tell you what the margins for certain industries are, right? I can only tell you from a hardware perspective. So if we want to have accurate predictions, we need collaboration. And people might say, it's a fool's errand to predict the future, but what the fuck is the fun in that, I say, if you're going to have any sort of fun with this whatsoever, right, you got to make grand statements. So collaboration is what we need, right? So it's like, hardware is my domain, but if any of you guys have expertise beyond that, in the realms of whatever it be, quantum or economics or whatnot, I greatly value any input you guys might have, and we might have a model that more accurately predicts the future. There'd be a GitHub where I've published a lot of these references and papers. These are the areas for which, like I said, I am not an expert, and if you are, I would welcome any sort of input that you do have. And that is our talk. John Lynn. By all means.
You mentioned it was a 4-hour version of this?
It should be online somewhere.
Somewhere.
It's on YouTube somewhere. I got to find the link though. I gave it at I think it was like a hardware consortium, so they were the ones that recorded it. But yeah, I go into more technical details in that one, and I'm a lot less drunk, so it's very different tone.
How about the presentation itself? Is it available somewhere?
Yeah, this one is on the GitHub that I've just posted. I'm sure they can link it in the meetup page, but yeah, you can find all these slides there. Although I think that's the outdated version. Oh, I'll update it with the new version, yeah. So.
Yeah. So I have a bunch of questions, but first of all, thank you for the talk. I would say it's like really thought-provoking because every slide requires actually a great explanation.
It's very dense. I get that.
So
we only had an hour, so.
Okay, I have some idea of the first part. So.
I mean, the first time I gave the talk, I was like, guys, try not to blink because I don't have time to explain each slide.
Yeah, but I have a bunch of questions.
By all means.
So let me start like for the first one, and like I can continue if nobody has ours. So first of all, if we go to the hardware, basically like the whole thing was designed with the assumptions that we need like general computing, and it's like traditional computing of like operating with bits and bytes, with like instructions, etc. Like and building transistors to build NAND blocks to build like traditional memory, etc. Like, is it mostly like the cause of like the market requirements or our like exploration into different fields of different designs?
So
like, why should we design our hardware in a certain way, like to work on like instructional level?
It's overhead, right? So it's like it doesn't scale well if you have it too customized, right? So obviously you need instructions that scale. You need, because a lot of hardware is like very redundant chips. Because when you do like that's just the logical side. When you do like place and route at such low levels, right? It's very expensive to ask the guys, okay, hey, I made a tiny little tweak here, reroute everything, right? So it's like you have a lot of modularity, you have a lot of overhead, a lot of repeating patterns, right? You need a lot of design that's reusable, right? So.
Okay. Is there any other, like on basically like atomic molecular level, any other design?
There is an approach called, there's an approach that uses gold nanowires that basically they use like electrical stimulants to basically have it configure itself into a model that computes something very, very accurate to what you want. But understand, that's not going to scale well, right? Like sure, you can design it very, very custom to what you want at the molecular scale. But when it comes time to actually mass produce that and fabricate that, that's a bottom-up design process, right? You're customizing it using external stimulus to get it to configure itself. Anytime that you need to scale, you need to use a top-down design process, right? You got to use the repeating patterns. You got to use the same, because like you have minimal ways of controlling stuff when it's that small, right? So, like I said, they do exist, and I'm 100% sure they're going to stay in the lab for indefinite time.
Yeah. I also wanted to ask, like basically right now the approach to memory is mostly like, okay, we have a unified memory shared between CPU and GPU, and it's like dynamic memory, obviously. Mm-hmm. But like in LLM, specifically in AI context, like the weights are mostly static. So is there like approach where we can kind of like encode that and make them only readable memory?
Sorry, your question is, can you encode the weights of an LLM into dynamic memory? I mean, they
encode in more efficient, like read-only memory and supply it to like servers which use like exact models.
There are analog approaches that do this, right? Not digital ones, because obviously there's a lot of bottleneck when it comes to interfacing the two. There's like analog approaches where they use I guess DRAM and only DRAM, right, for the the neurons, right? And a lot of those, I wouldn't say they're read-only. The only read-only models we have are very, very large scale, not very small scale, right? It's just not economical to produce read-only memory at that scale and have them neurons map so precisely, because you're not going to update that very often. But I would say, yeah, they're all analog machines. They're only very large scales. You will see that sort of model. It's just not practical to have them at the nanoscale. The closest that you have is like a DRAM cells as neurons, and that's technically read-write. It's not read-only memory.
Okay, we got to call it here, but we can continue the Q&A in the other rooms.
All right.